Alright, so the first topic we're looking at today is Serre's theorem. So essentially we're taking that same Lie algebra structure we saw before, being generated by a series of generators and relations informed from the root system. And this time we're adding on the we only used the first three last time. We're adding on the fourth condition here, which, as we can call, is based off of we'll see it here. We're going to set xij to be the adjoint of xi to the copy of negative of the Cartan integer cji plus 1 on xj, and yij to be equal to the adjoint of yi. It's the same thing except on y and j. And of course I and j have to be distinct in these cases. And so this brings us to our first lemma, which states in L0, which is the algebra we set up last video, the adjoint of kx for yij, with of course ij distinct, has to be, is 0. The proof. I don't know why I started the proof, writing the proof there. First case is the index of our k doesn't match the index of our x doesn't match the left index of our y, in which case our second restriction gives us that xk bracket yi equals 0. So the adjoint kx and the adjoint yi commute. Therefore, we get that from the above relation. The adjoint of x of k on y of ij is the adjoint of yi to the negative c ji plus 1 times the adjoint of xk on yj. If k equals j, then this is the adjoint of yi to the power of negative c ji plus 1, as always, on hj. But by constraint 3, I don't know if constraint is the term I used last time, but 3, the adjoint of yi on hj is Cartan integer cij times yi. If this is non-zero, then cji is negative. so that minus cji plus 1 is at least equal to 2. Thus, the adjoint of yi to the negative cji plus 1 on hj equals 0. If k is not j, on the other hand, then xk with yj is 0 by constraint 2, and then we proceed as before. The second case, in this here though, is when k is equal to I. If we showed last time that, recall that our S decomposes into our field scaling x, S being set equal to our field scaling xi plus our field scaling yi plus our field scaling hi is a subalgebra of L0 isomorphic to SL2 of F, which gives us a little info about the adjoint action of S on L0, even though L0 might be infinite dimensional. Since j is not equal to I, the bracket of xi and yj is 0, so yj is a maximal vector for S of weight, what we're going to label m, which is equal to negative cji as the bracket of hi and yj is equal to negative cji yj. Induction on T gives that the adjoint of xi on the adjoint of yi to the t on yj is equal to t times m minus t plus 1 times the adjoint of y I to the t minus 1 on yj. Thus, the right hand side of this is 0 when t is equal to minus cji plus 1. That's the end of our proof. There's one more idea we need before we get to Serre's theorem here. We're going to call an endomorphism x of an infinite dimensional vector space V locally nilpotent if every element of V is killed by a sufficiently large power of X. So that in this case, X is nilpotent on every finite dimensional subspace. I'm going to say W and V. So we can define the exponential of X restricted to W. Since the exponential of X on W and the exponential of X restricted to a similar W prime agree on the intersection of W and W prime, we can define an automorphism EXPX, which they have in scare quotes, of V. Alright, this brings us to our theorem, which is serre. So we're going to fix what I'm guessing is an axiomatic root system. Fix a root system phi with base delta being a collection of alpha I from 1 to L. Let L be the Lie algebra generated by the 3L elements xi, yi, zi under, they call them relations, probably the better term. I call them like constraints or something, 1 to 4 from before. And then L is a finite dimensional semi-simple algebra with a Cartan subalgebra spanned, oh yeah, it's supposed to be HI by the, not what I called ZI here, HI. And a root system of course, our phi. So, proof. We're going to start out with some definitions. We're going to have L zeros before. We're going to let L be L0 over K. I guess it's more just notice. We already defined L. L is our L0 over K, with K the ideal generated by all xij and yij. And we're first going to work inside L. We are going to start inside of L0. Let I/j, I'll use double slash, note that these are, I'm just separating these and not, because I noticed it got kind of confusing, to me at least last time. Let I, alternatively j, be the ideal of x, or alternatively of y, generated by, that's real bad. Generated by the xij, alternatively the yij. Alright, our first step is that I and j are ideals of L0. We're going to consider ji as analogous. Note that yij is an eigenvector of the adjoint of hk with eigenvalue of cjk plus cji minus 1 times cik. Since the adjoint of under hk of y is within y by the Jacobi identity, we get that the adjoint of hk of j is in j. On the other hand, the previous lemma says that the adjoint of xk of yij is 0. As the adjoint of xk maps y into y plus h. We get with our previous results that the adjoint of xk preserves 8, maps j into j. And once again, by the Jacobi identity, the adjoint of L0 then must map j into j. And we have, as I said before, similarly for I. Our second step in our proof is pretty straightforward, that k is equal to I plus j. By definition, we have that I plus j is within k. Note that I plus j is an ideal of L0 containing all xij and yij, and K is the smallest such ideal. Alright, step 3 is that L is equal to n minus plus h plus n as direct sum of subspaces, where n minus is y over j, n is x over I, and h is identified with its image under the canonical map L0 into L. This is by step 2, along with direct sum decomposition. L0 is y plus h plus x, which we saw last time. Four is that the sum of fxi is the sum of fyi plus the sum of fhi. They put h first. I guess it kind of makes sense. Not that it really matters. Maps isomorphically into L. This is as in step 3. Since H itself maps isomorphically into L. We may therefore identify our x, y, and h with elements of L. And these, of course, generate L. Step 5, that f lambda is in the dual of h. Let L lambda be the x in L. This is one of these that kind of like that you prove it in defining it, what you're proving. Where the adjoint of h on x is equal to lambda of h on x for all h and h. So this is essentially the elements in L, which when acted on by elements of h have lambda as a character function. Then h is L0. N is the sum of our roots of our L lambda for positive lambda. And minus is the sum of our L lambda for negative lambda. And at each L lambda is finite dimensional. And this is direct from our previous two steps. Okay. Next up is number 6, which is for each I, of course, the adjoint of xi and the adjoint of yi are locally nilpotent endomorphisms of L. And we're of course going to consider just one such element from one of them, and everything else is going to follow by symmetry. So let M be the subspace of elements of L killed by, I don't know, I'm suddenly going to rewrite it, killed by a power sufficiently large, of course, of the adjoint of our, say, xi. If x is an M, if x and y and M, sorry, it got hard to read for a second, is killed by adjoint of xi to the r and adjoint xi to the s, then their bracket x comma y is of course killed by the adjoint of xi of r plus s. So M is a subalgebra of L. But we see that all xk are in M by relation 4 for A, and all yk are in M by relations 2 and 3. As these generate L, M is equal to L. Alright, step 7. This is another one that's immediate. Taf I as the exponential of the adjoint of xi, defined in our previous manner, in our preamble, flanking the exponential of the adjoint of minus yi. Adjoint xi is a well-defined automorphism of L, and this is by part 6. Part 8, how many parts are there? I think there's 14, so we're halfway there. If we have two elements in the dual of H and with sigma of lambda equaling mu for some sigma in the Weil group, then the dimension of L of lambda is the dimension of L of mu. Assume without loss of generality that our element of the Weyl group is a simple reflection because it would generate the Weyl group. Then the TAFI we constructed in the last step coincides on the finite dimensional space L lambda plus L mu with the ordinary product of exponentials So Ti, as we've seen something vaguely similar like this to this before, and it'll interchange L lambda and L mu. Which means they have the same dimension, of course. Step 9 is that the dimension of each L alpha I, for alpha I being an element of our base, of course, as before, is 1. For alpha, hang on. While on the other hand, L of k alpha I is 0 for k not being -1, 0, or 1. So this is clear for L naught and by step 4, which was this. Step 10. This one that mixed me up before. If alpha is in our root space, the dimension of L alpha is 1. While dimension of k alpha is 0 for k not in -1, 0, 1, as each root is Weyl conjugate to a simple root. So this is by steps 8 and 9. Step 11. If the eigenspace with character lambda is non-zero, then lambda is a root, or it is 0. Otherwise, lambda would be an integral combination of simple roots with coefficients of like sign and lambda lambda not a multiple of any root by our previous step. By an exercise we're not going to do in this video series, some vowel conjugate sigma of lambda has a strictly positive and a strongly negative. Strictly negative, not strongly. My brain's not working here. Strictly negative coefficient. So L of sigma lambda is 0. It's contradicting 8. Against, because 8 says that it has to have the same dimension. So says that the dimension of L is our indexing L plus the cardinality of our root system. By 5, 10, and 11. Okay, step 13 we're going to need to do on a new line, so that's pretty exciting. Step 13 states L is semi-simple. Let A be an abelian ideal of L. We want that A is 0. Since the adjoint of H stabilizes A can be written as the sum of its intersection with H plus its intersection, the sum of its intersections with each root in our root system. As L is H plus A likewise sum of these L alphas. If an L alpha is an A, then the bracket of it with its negative space is an A. So L negative alpha needs to be an A. And A contains a copy of the simple algebra SL2 of F, which obviously can't happen. So instead, A is equal to A intersection of H within H. So the bracket of L alpha with A is 0. So A is inside the intersection of the kernels of each root, which is 0 as the I's span H star. Step 14, I believe this is our last one. Not 100% sure on that though. L has a Cartan subalgebra H with root system being our axiomatic one. H is abelian, so is nilpotent. And self-normalizing. Self-normalizing from L equaling H plus the sum of our L alphas. So H is a Cartan subalgebra with, obviously, it's going to have roots of V. The next chapter is really small and really important, so we'll just do it here. And this is existence and uniqueness theorems. Alright, this is pretty, it's just one theorem, but it's obviously going to be kind of the point of what we've been doing for a while here. Part A is let phi be a root system. Then there exists a semi-simple Lie algebra with root system being equal to phi. So for any root system there exists a semi-simple Lie algebra corresponding to that root system. Part B is let L and L prime be semi-simple algebras, Lie algebras, with Cartan subalgebras H and H prime, and root systems phi and phi prime. That isomorphism from phi to phi prime sending a given base delta to delta prime, and denote by pi from H to H prime the associated isomorphism for each alpha and delta, alpha prime and delta prime. Select arbitrary non-zero x alpha and L alpha and x alpha, x prime alpha prime in L alpha prime. There exists a unique isomorphism pi from L to L prime extending our previous pi from H to H prime with pi of each x alpha being x prime alpha prime. the proof. For step A, this was what we did in the last theorem. For step B, I'm going to choose y alpha prime, such that x alpha, the bracket of x alpha and y alpha is h alpha, and likewise for the primes. And this one is actually going to be equal to, see that, pi of h alpha. Since the x prime alpha prime, y prime alpha prime, h prime alpha prime satisfy our previous theorem, which defines L, is a unique homomorphism pi from L to L prime, sending each x alpha, y alpha, z alpha to x prime alpha prime, y prime alpha prime, z prime alpha prime. H, why do I always call H Z? H alpha to H prime alpha prime. And then this pi extends our pi from H to H prime. And this also yields, can also be used to make a homomorphism pi prime from L prime to L, which is a two-sided inverse for pi. As the composites are the identity maps on the generators, so pi is an isomorphism. Thus we finally have a one-to-one correspondence. We have a one-to-one correspondence between our root systems and our semi-simple Lie algebras. Oh, it looks like up next we'll be characterizing simple algebras, like looking at the 5 exceptional ones, I think. We're looking at, not quite. We'll be looking at G2 and the simple ones, I think. Yeah, we won't be looking at E's and F's. But anyways, that's our concern for next time. For now, we can call it here, I think.